So well, the summary of what I've been teaching during the last 4 classes is shown here. So thin films can be in again, just a minute. I need some more requests for admins. Okay, right. So thin films can be in single crystalline form, and polycrystalline form, and completely non-crystalline form. A non-crystalline form is called the amorphous form. And so apart from these 3 forms, thin films can also be in nanocrystalline form. So which means a single material can be, so I take silicon or gallium arsenide, gallium nitride, zinc oxide. I can get it in a single crystalline form, completely amorphous form, polycrystalline form, and a nanocrystalline form. Non-crystalline form is, of course, amorphous. Okay. Now, going back to the 4 categories: ceramics, metals, alloys, and intermetallics. Just to give you a quick example, I mentioned about superconducting intermetallics, Nb3G and Nb3 vanadium, 2 examples of intermetallics, which I defined intermetallics as line phase compounds. And these line phase compounds give rise to a given property only for a specific composition. Any deviation from the line phase compound, the property is lost, which is not the case with alloys. Ceramics also are line phase compounds. So I give the famous example of yttrium barium copper oxide. I said why Ba2Cu3O7. Only for that composition, the cationic ratio of 1, 2, 3, and oxygen ions present in the lattice in a specific way would make that ceramic, which is supposed to be an insulating compound, a metallic superconductor. So I also mentioned that at various points during the course of this course, I'll be citing the example of yttrium barium copper oxide to understand the crystal structure aspects, anisotropy in physical properties, etc. But if you take the conventional superconductors, the low temperature superconductors, I just want to highlight the type of applications that you see when the same material is obtained in different forms. So these are, what you see is a bundle of wires made out of superconductors, like NBTI. And so drawing them into long enough wires itself is a challenge. And these are used as power carrying cables. But then if you want to use the superconducting property where the resistance during the flow of current charge is 0, then you need to cool these wires down to those temperatures, right? But then, of course, that is required for various applications. Typically, a superconducting transition, because superconductors show normal metallic state resistivity. There's a drop in resistivity or resistance as a function of temperature. This is a resistivity scale, and this is a temperature scale. And below a certain temperature, the transition, as you can see here, touching the y-axis means it has attained the superconducting state. And a superconducting state is accompanied by a wonderful magnetic property that is called the Meissner effect. The magnetic state of a superconductor is a perfect diamagnetic state, which means the same superconductor for which I do an electrical property measurement, rho, resistivity as a function of temperature, if I do the magnetic property measurement, that is, if I measure chi susceptibility, magnetic susceptibility, what I see is a very interesting phenomenon called Meissner effect. Meissner effect is nothing but this black block here is, in fact, yttrium barium copper oxide, which is in its polycrystalline form. I'll explain what polycrystalline it is in this particular case. And I also mentioned in the last class, remember, even though this unusual ceramic attains superconductivity and shows zero resistivity or zero resistance at 90 Kelvin, but the current density is an issue there. It means the current carrying capability of this block or the material made in the form of a wire or a thin film is largely different from the conventional materials like copper, aluminum, and other alloys. We'll see what that problem is due to. Okay? And I also said that problem, the current density, which is 10 raised to 2 amperes per centimeter square, shoots up by almost 4 orders more, becomes 10 raised to 6 amperes per centimeter square. If the same polycrystalline yttrium barium copper oxide is obtained in the form of a single crystal or a thin film, right? 4 orders of difference in the current carrying capability. And of course, the superconducting transition is shown in all the 3 forms. Whether I get yttrium barium copper oxide in this block form, that is polycrystalline form, or a single crystalline form, or a thin film form, I see the superconducting drop. That means that is the property of yttrium barium copper oxide showing superconducting behavior. But the next property, that is, current carrying capability, how much maximum current a material can carry, that depends on the internal microstructure of the material. That's what I'm coming to, right? So between polycrystalline and single crystalline systems, by definition itself, I said polycrystalline is a conglomeration of large number of crystals. That means between 2 crystals, there is a unwanted boundary. That's why it's called a polycrystalline material, which means in single crystal systems and thin films, we are eliminating those grain boundaries, right? So that's the crux of the whole, the matter about thin film growth. Okay, quickly, what the Meissner effect is, when it shows zero resistivity here, when you bring of course, you can see that, this superconducting block is cooled in liquid nitrogen, right? The liquid nitrogen is sufficient for me to cool it and take it down to its superconducting temperature. I mean, this can be demonstrated at the lab level also. I can do it on a tabletop. I can afford to burn away a lot of liquid nitrogen because the moment you pour it on a small piece of superconductor, the room temperature starts vaporizing the liquid. So what you're seeing is the nitrogen gas that is formed. In fact, this is one way of producing pure nitrogen. For MEMS fabrication, people actually use, when nitrogen is required, they produce nitrogen from liquid nitrogen. They take liquid nitrogen and then boil it off, and they get pure form of nitrogen. So what happens here is you take this superconducting block, you bring a magnet close to it. So before the superconducting state here, right, the magnetic field lines flow through the superconductor, but the moment you hit the superconducting transition temperature, the block gets into its superconducting state, no magnetic field can penetrate through the interior of the superconductor. That means the magnetic induction is 0 inside. So that will sort of, you create, the superconductor expels all the magnetic flux lines from the interior, and the result is what is called the Meissner effect, where the superconductor starts hovering on top of the the superconducting block. This is a fantastic magnetic levitation effect. Okay. That's how it happens. This is exactly the scenario inside when the superconducting transition is reached, but before the transition, right? all these magnetic flux lines flow through the superconducting body like the magnetic flux lines do in any other magnetic system. Of course, if it's a ferromagnetic material, all these magnetic lines are more packed into the ferromagnetic material compared to a normal paramagnetic system. But in a
Sir,
yeah,
sir, I have a doubt, sir. I'm
yeah,
Tanvir.
go ahead.
So you said no magnetic
Field lines,
field lines pass through the material. So
yes,
what if I apply extreme magnetic fields, or like of?
exactly, yeah. So
So I have.
see, extreme magnetic fields that can kill the superconductivity. In fact, magnetic field and superconductivity are enemies. Okay,
Okay, sir.
which means there is only a certain amount of field that the superconductor can repel.
Okay, sir.
Right. So exactly, like I said that a superconductor shows this transition, whether it is in any of the forms, that is polycrystalline, single crystalline, and amorphous form. Okay.
Yes, sir.
Right. But I also said if I try to push in more and more current through a superconductor, right?
Yes, sir.
Through a polycrystalline system, the current density, I said, it's just 100 amperes per centimeter square. But this value is 4 times more in a single crystalline form of the same material, right?
Yes,
4 times more. So that means what? The critical current density of the same superconductor
yes,
in the
sir.
bulk form and the single crystalline form are different.
Yes, sir. Yes,
The
sir.
same critical current density also applies here. But in this case, I call it the critical magnetic field.
Okay, sir.
So let's say, see, what you see here is a small circular magnet, cylindrical magnet, whose magnetic field strength could be 1,000 oersteds, right?
Okay, sir.
Now you change it to 2,000 oersteds, 3,000 oersteds, 4,000 oersteds. Depending
Yes,
on
sir.
the type of this magnetic system, magnetic field, there is one thing you should all realize, that is the schematic that is showing here is, it is not showing any single line penetrating through any part of the superconductor. But in reality, a few magnetic field lines always flow through the periphery of the block. And that is called, to an extent of about a few angstroms to nanometers. And that depth to which a magnetic field flows through, in spite of the fact that the rest of the superconductor expels the magnetic field out, is called the penetration depth. It's exactly like the skin depth in metals. No,
Okay, sir.
skin depth is a few microns in metals, but here the penetration depth of the magnetic field is a few nanometers. But then there are two types of superconductors, type 1 and type 2 superconductors. Type 2 superconductor is, the moment you reach the critical magnetic field, it loses its superconductivity. That's it. It's no more a superconductor. Type 1 superconductor. In type 2 superconductors, there's a first critical field, second magnetic critical field. That means as you reach the first critical field, is it clear? The first type of type 1 superconductor, there is only one magnetic field above which the superconductor becomes a normal conductor, normal system. There's no superconductivity, because if the magnetic field, if critical magnetic field Hc is say 1,000 oersteds, if you apply more than 1,000 oersteds, the superconductivity is lost. Which means what? You don't see this levitation effect. The magnet stays on top of sits on top of this block, because it's not, the superconductor is not repelling the magnetic field anymore. But in type 2 systems, you go beyond that. There is critical field 1 and critical field 2. In some cases, critical field 3 also. So you go beyond the critical field 1, you call it HC1. You still see this effect, but in spite of the fact that the magnetic field starts penetrating through the system, right? That's how you distinguish between two types. But the result is, the answer to your question is yes. You cannot indefinitely have larger and larger magnetic fields. That depends on the volume of the superconductor, or volume of this block that you initially start with. Okay.
So, And you said type 1 and type 2, right, sir?
Yes, yes.
So how exactly you can classify the material based on type 1 if it's type
Yeah,
1?
yeah. So if you do a simple like what the plot you see here. This is a typical rho versus T, resistivity versus temperature. In a similar way, I do chi, magnetic susceptibility versus temperature, and I also have to do magnetization as a function of magnetic field. Doing
Okay.
these two experiments, I'll be able to classify which is a type 1 superconductor and type 2 superconductor in
Okay.
terms of applying magnetic field. By doing electrical resistivity measurement, you won't be able to distinguish between type 1 and type 2, but type 1 and type 2 can be determined only when by doing a magnetic field measurement,
Okay,
right?
sir.
Right. More details are not required here, but that is taught in a regular condensed matter physics course or course on superconductivity. But if you want, we can discuss at a later time also. All right.
Sure, sure.
You see, the yttrium barium copper oxide example that I gave has a structure, crystal structure like this. No, till now I mentioned about a simple cube where imagine a cube where a cube of equal side lengths with 8 atoms sitting at 8 corners, and then you have a next type where one more additional atom is at the body center and so on. But here you see how complicated this looks like. It's a very complicated structure. And the most interesting thing is these properties that I'm showing here, they come from the way atoms are arranged in this complex structure, right? Then I also mentioned about the kind of applications that we have with a single system like yttrium barium copper oxide, various space applications, microwave applications and all that. But for that, you need to get it in a single crystalline form or a thin film form. Now imagine if I have to make this structure to sit on a stable surface, on a substrate, and to grow these unit cells, oh, that becomes a big challenge, right? The whole thin film growth process is to meet those challenges, right? So yeah. So quickly, again, just to highlight the kind of you know applications that one can see just with a simple superconducting system itself. You can draw them into wire form like this, to use them as current carrying cables with a large number of current density. These are all from conventional superconductors. These are used in generators. And then if you use this superconducting wire and wind it in the form of a coil, you make a superconducting magnet. See, the normal electromagnets you must have all seen at various levels in BTech labs and in MSc PG labs. You must have seen an electromagnet. An electromagnet is basically is made by winding a copper wire. You know that, right? You take a copper wire and wind it, and the magnetic field, Biot-Savart law, and the magnetic field can be calculated with the amount of current that is flowing through the coil, right? I have and also the number of turns. Basically, it's your H is equal to Ni by L, where N is the number of turns, I is the current that is flowing through it, and L is the length of the coil, right? So it's not that you can produce infinite field of magnetic field by increasing the current that is flowing through these coils. No, there is a heating effect there. So the current that is flown through a set of coils is limited by various factors. It's limited by the gauge of the wire that is used to make that coil. So that's why if you see an electromagnet, even to produce 5,000 oersteds, right? What is the higher value of a magnetic field? Anybody knows? I'll tell you. If I insert this slide here, so yeah, see, that's what I'm doing. coil, a passive current. So I can easily produce a magnetic field because your H is equal to Ni by L. Then you can't pass large amounts of current in order to increase this magnetic field because there's a heating effect. So the the normal electromagnets that you see in the labs, yeah, there are those poles there, and there are windings inside each of these coils in opposite direction. And what are the maximum fields that you can produce with electromagnets? So the maximum field that you can produce with electromagnets is, at the lab level, is a maximum of about 2 Tesla, 2.5 Tesla. And 1 Tesla is 10 raised to 4 oersteds. It means 10 to the power of 4 oersteds. 10,000 oersteds. That's a large unit. That's a huge amount of magnetic field. Compared to this, the Earth's magnetic field is, do you remember Earth's magnetic field? It's anywhere from 0.35 to 0.65 oersteds. Such a small field it is, right? Okay. Now, so the Earth's magnetic field, so the larger unit is Tesla. I also have the smaller units in terms of oersteds and Gauss. So when we talk about Earth's magnetic field, which is so small, of course, 0.35 to 0.65, is it the unit is oersteds or Gauss? When do we use oersteds and when do we use Gauss? Does anyone know? When we use oersteds and when we use Gauss? So when I talk about Earth's magnetic field, should I say it's 0.35 Gauss or oersteds? Think about it and tell me. Okay. Anyway, so now the point here is to construct an electromagnet that you see in the lab. So the lab electromagnets that are used to do a typical Hall measurement, Hall effect measurements is not more than 2,000 oersteds. 2,000 oersteds. So maximum you can go is 2.5 Tesla. To get a 2.5 Tesla electromagnetic field, 2.5 Tesla, 2.5 into 10 raised to 4 oersteds of magnetic field. Now the coil diameter itself will be more than 1 meter, which large number of turns of copper, right? You can actually calculate and see for that diameter how many turns are required, and what should be the gauge of the copper tube or copper wire that needs to be used. And of course, to get 2.5 Tesla, you need to be passing a significant amount of current to these coils, almost of the order of few 10 to 20 to 30, 40 amperes of current, depending on the field that you want to generate. So the limit of 2.5 Tesla is basically on the diameter of this coil, and also the upper limit of current that you can use. You can't, I can't pass a current of 200 amps through even a 1 centimeter dia copper tube, or it's in the rod form. So the maximum current you can pass through is say if it is 40-50 amperes to get 2.5 Tesla, and there is a lot of amount of heat generated during the flow of this current. So you need to take that heat off. So these electromagnets with these huge coils, they also have this water circulation to dissipate, take the heat away continuously. Otherwise, the whole coil assembly can get burnt. But then, look, If 2.5 Tesla is the maximum upper limit, in fact, with an electromagnet, you can push this limit to 3 Tesla. How do you produce larger fields? Because if you go to this picture now, I'll come back to the first one. Okay. Yeah. You know this, right? This is a magnetic resonance imaging setup. Right? For body tissue scans, this is used. You know, if a brain has to be scanned, you send the patient inside. There's a huge magnet there, and MRIs require the beginning they used fields in excess of 7 Tesla. Then they found that 7 Tesla is not good for human body. Today's MRIs operate at 4 to 5 Tesla. They still want to reduce that field down to 2 or possibly 1 Tesla, so that this magnetic field will not have any effect on the tissues and especially blood. Blood is our human blood is diamagnetic, so it can start splitting up when you use extremely high magnetic fields. But when I'm talking about 4 Tesla of magnetic field, I'm not talking about electromagnet anymore, because there the limit is just 3 Tesla. That's where superconducting magnets are required. You see, the beauty about these superconducting magnets is, if you take a bunch of those superconducting wires, wind it into the form of a coil, right? I said to get a 3 Tesla electromagnet, you need a huge amount of, huge coil, and this coil, through this coil, you're passing a large amount of current. But here, if you look at the size of this, probably this is from lengthwise, it'll be about say 12 inches and 6 to 7 inches across, and the diameter of the bore there is about 1.5 inches. That's all. In this short volume, to wind a coil about 2,000, 3,000 tons of superconducting wire, you get a magnetic field of 5 Tesla easily. 5 Tesla. So this is a beauty of using superconductors now in the form of wires to get high magnetic fields. And high magnetic fields are required, one, for basic research. I mean, there are 2-3 labs around the world that always try to push the limits of maximum achievable magnetic fields. And today, what is the maximum achievable magnetic field? It is 42 Tesla. There's one in Tallahassee in the US and one in Japan. They keep competing with each other. From 42, they reported 42 last year. But any magnetic field about 20 Tesla is only for, can only be produced as a pulsed magnetic field. You cannot have a continuous magnetic field. So there are some, to look at some fundamental aspects of electronic correlations in solids. You take a material in a single crystal form or a thin film form, and you want to subject the atoms and electrons that form the lattice to extreme temperatures to look at some very fundamental phenomena. For that, you need extremely high magnetic fields. And you also need high magnetic fields for these kind of applications, MRI. And most interesting application is is just a part of the LHC, Large Hadron Collider. And the synchrotron radiation circles, where this Large Hadron Collider, you see, it's a long tube that goes around with a very large perimeter of a few kilometers, and you're accelerating particles through it, right? And first of all, you need magnetic fields at every juncture in order to bend the beams, particles. One. Second, if you look at the diameter of this tube here, the diameter could be twice the height of a normal person. It's close to 10 feet, in diameter. These tubes have to be kept in vacuum continuously. So that's why to build these experiments to see Large Hadron Colliders are used to, I mean, billions of dollars were spent finally, the existence of presence of production of bosons was detected, the Higgs boson. But then the experimentation that goes into it, because the vacuum, to build a system like this with perfect vacuum, with minimum of vacuum leaks. I said vacuum technology is so important for thin film growth. It's very essential here. And magnetic fields at different junctures to bend the beams. You see? And of course, we talk about this maglev trains. It's all about using superconducting magnets in maglev trains. Okay. Without that, these huge enough fields cannot be created on the track and on the base of the train to create this that levitation effect. And of course, just another quick example is today you take superconductors in thin film form. This is just an example of conventional superconductors, NB and aluminum, made in the form of thin films. There's a Josephson junction made there. Don't worry about what a Josephson junction is if you don't know. Deposited using physical vapor deposition technique and to fabricate the superconducting qubits, quantum bits. You see the wide range of applications of just one superconducting system itself, all the way from superconducting qubits to low field, high field magnets to superconductors used in microwave devices. Yeah? Well, so I mentioned this to you that it's the basic building block, that is a unit cell, plays a crucial role in bringing about all these properties. Whether I talk about superconductivity, a piezoelectric property, or a magnetic property, everything comes because from the unit cell and the way atoms are arranged there, and what happens to the electronic correlations, the electrons attached to these atoms. An example of the basic unit cell of iron, the basic unit cell of magnetite. Anyway, I keep telling all the time, there is no condensed matter physics. You'll never be able to understand anything about condensed matter physics if you do not understand how the crystal structures form and what are the electronic correlations there. It's very important. Crystallography plays a very crucial role for us to understand all physical properties. Yeah. So what I show here on the left side is a ceramic powder, right? Ceramics, again, going back to the definition, inorganic, non-metallic compounds processed at high temperature. And when you make a ceramic, you get it in a powder form. And these powders can be used to, you can convert these powders into compact blocks, because if I want to do any physical property measurement, I can't do physical property measurements on these powders. Some experiments can be done. If I want to do a spectroscopy, I can take a small pinch of this powder and do a spectroscopy measurement. But if I want to do an electrical property measurement, then I need to compact it. That means I put it in a die and plunger, apply high pressure. That means I bring all the particles together by compaction, by applying high pressure. But that itself is not sufficient. I should make the particles to coagulate. That's where I need to heat the compact at a certain high temperature. And when you heat it, you get a material in a compact form. But that compact form will always be in a polycrystalline form because it is an agglomeration of a large number of particles. Okay. But I can also convert this ceramic powder into a single crystal, right? So there is a separate single crystal growth process. You see, what I'm showing here is just a piece of metal. By looking at it, if I ask you what kind of a metal it is, you'll name it as copper. We all know how copper looks like. We know, you can recognize gold, silver, right? And this is a typical metallic luster of copper. And if I ask you, and then I show you a ceramic piece like that, exactly like what I've shown in the previous slide of the superconducting block. So normally insulators have a dull looking surface. The surfaces are not shiny. But then, so if I ask you which one of these two would be a good conductor, you will say, of course, it is copper because it's shiny. Metals are shiny and they also conduct electricity well, better, because you have free electrons there. And if I also ask a question about which of these two would be a good thermal conductor, your answer would again be copper, because we also know that good metals are also good thermal conductors. Good metals are good electrical conductors and also good thermal conductors. So the conclusion about this block would be, yeah, it looks like a ceramic, so it should be non-conducting. No, it might turn out to be a superconductor. So an unconventional ceramic, which is not a metal, can acquire metallic properties by process of doping or whatever, and then it can lead to exhibiting superconducting properties. Right? Yeah, and you see again a bunch of carbon atoms arranged in a specific manner gives rise to a structure called diamond structure. We know the value of diamond. Even before crystallography was born, people had attached a lot of value to diamond, because diamond was mined first in India 4,000 years back. But we came to know about the existence of atoms only 100 years back after crystallography was born. Okay, but again, you know that, so this is a good electrical conductor and also a good thermal conductor. And this turns out to be a surprise. Oh, it's not so shiny. It must be an insulator, but it could be a superconductor. So diamond, for example, we know that it's one of the it's a hardcore insulator. If you take the valence and conduction bands of diamond, they're separated by more than 5 electron volts, and so the band gap is so huge, it is an insulator. But so can insulators be thermal conductors? Normally, no. But the best thermal conductor, of course, is copper. We know that. It's about a thermal conductivity in terms of value is about 400 watts per meter per Kelvin. But what about diamond? It's an insulator, electrical insulator, but its thermal conductivity is 5 times more than that of copper. This is just amazing. A diamond has the largest, highest thermal conductivity of any other, compared to all the materials in the table of thermal conductivity. This is just amazing. This is 4 times more than that of copper. So which also means that thermal conductivity not only comes from the contribution of electrons, it comes from something else, because diamond being an electrical insulator, there are no free electrons there. So here, in the case of diamond, thermal conductivity arises from the contribution of phonons. The phonon contribution is so strong that even though there is no electronic contribution, the phonon contribution completely predominates. Its electronic contribution is 0 here, whereas here it's both electronic and phononic contributions. And this insulating diamond, which has a band gap of 5.3 electron volts, today you can dope diamond with few specific elements like boron, phosphorus, nitrogen, and make it into a superconductor. Can you imagine a diamond, an insulating material driven all the way to metallicity and then showing superconductivity? This is a beautiful insulator to metal transition, right? This is where you talk about correlated electronic systems, no? The correlation effects. Then we have this the Morse theory to explain how an insulator transforms into a conductor and a superconductor with the doping, etc. Okay. So what we have seen, a simple question like which of these two will be a good electrical conductor? Anyone would answer that copper is a good electrical conductor. And that's just an educated guess. You don't have to be a scientist to say that. But And if I ask you about a physical property of this, we might just be able to say that it looks like a ceramic powder, but you will be able to say nothing about its physical property. So that's all you can say by macroscopically examining or looking at a material system. Then you go one step ahead, get what is called the microstructure. That means you take this block of yttrium barium copper oxide, which I said is a ceramic. A ceramic is obtained from a powder. So I take these powders are compacted, and the compact is heated, and then it looks like a nice compact with a shiny surface. But the reality is, if you put it under an electron microscope, this is what you see. This is a beautiful textbook image of how a ceramic looks like. No? So it has all these large number of grains. Each grain is a single crystalline region. That means the unit cells are arranged. See, for me to call it a single crystal, again, by looking at it, I can't say. By looking, this could be a piece of glass. So if you take the glass pane, break it, you get a small piece of glass. Yeah, I can show it here. See, this is a beautiful crystal. This is a natural crystal of quartz. Okay. Now, this is another crystal. You see the crystal formation here? It's a naturally formed amethyst. You see, inside this small rocky piece, right? The crystals formed. Okay. Now, I can also show another beautiful crystal. Is that? Well, I can say that it's a crystal. I can even say that it is diamond. Exactly. It's like the picture that I'm showing here. You know, exactly like that. But this is just made of glass. Right? I'll be the richest guy if I have a diamond of this size. So this is just a piece of glass, but this is an actual crystal. So how do I determine this? I need to use crystallography. So microscopy also gives me some information about, yes, it is a granular material. It has large number of grains and grain boundaries, and even voids. You see those voids. These voids are completely missing material. The material is missing there. So now imagine you take this block and you want to do an electrical property measurement. Let's say this is a ceramic, and you know ceramics are insulators. I want to do a capacitance measurement. So I make a parallel plate capacitor and then put this dielectric in between because it's an insulator. I want to measure the dielectric constant, and I can measure the dielectric constant, but at the same time, if you measure the tan delta loss, the dielectric loss will be enormously high here because of these grain boundaries, because the charge that is separated, the charge formation, this charge will quickly start leaking through these grain boundaries and voids. So you can't make a capacitor out of it, number one. Number two, let's say this has a little semiconducting property, the ceramic block that you're showing there. Let's say it is a semiconductor, but it is in this polycrystalline form. So if I measure its semiconducting property, so electrical resistivity I do as a function of temperature, and I also do the electric. So let's say the same semiconductor is obtained in a polycrystalline form, which has grains and grain boundaries, and a single crystal form. And I measure the same property called electrical resistivity. What do you expect? We will see clear changes in the electrical resistivity value between the single crystalline form of the semiconductor and the polycrystalline form of the semiconductor, because when the current is flowing through this, right, current always flows through a least resistive path. And in this particular case, for the current to find the least resistive path is not a problem, but here it has to encounter the grain boundary energy. So that means the current has to even tunnel through these grain boundaries. But if the grain boundaries are widths are too large, then there's no way current can tunnel through. So obviously, the resistivity measured in this case will be enhanced because of the contribution from the grain bond, this grain boundary resistance, and versus having these voids. So if you want to do authentic physical property measurement, I don't want a material in this form, so I want to get it in single crystalline form, and much better for applications is get rid of these grain boundaries in a thin layer form. Okay, that is a thin film. Okay, so macrostructure and microstructure, but I can't again predict. I can only say yes. I see grain boundaries because I have a nice micro. This is required, of course. Microstructure has to be a part of research. Dealing with solid state materials, thin films, etc. Otherwise, you will never know about the way the grains and grain boundaries are formed. Okay, when I say grain, so I can actually count the number of grains here. See, there are large, small grains. We don't have a control on it because I made a compact and I put the compact in a furnace, and the nucleation process leads to the formation of grains, grain boundaries, and with specific grain boundary widths and all that you have. So this scale here reads 50 microns. From that scale, you'll be able to identify, find the, find the size of these grains. We have grains from 2 to 3 microns all the way to 50 microns. You see the variation there. So the most important thing is you want to go to deeper understanding the crystal structure. That's where crystallography plays an important role. And okay, now I know in the case of a material like yttrium barium copper oxide, yeah, I know that this is the way atoms are arranged, and these are the planes, these are the bond angles, bond distances. Today we have powerful softwares even to calculate the bond angles, bond distances. You don't have to go to neutron diffraction to do that. Earlier, that used to be the norm. But with simple X-ray diffraction itself, in the lab, you can get all these parameters about bond angles, bond distances, how bond angles change with doping and all that. But is that sufficient to understand more about the electronic correlations? If I want to know how these atoms sitting there, this yellow ball is interacting with the black ones around, or the red ones, what I have shown here, I've connected them, which means there is an interaction between the central one and these four, right? So to probe further in about these interactions, you need atomic structure. This is where spectroscopy comes in, and spectroscopy plays such a very, very crucial role. Today, spectroscopy has gone to a new level where I can just get a spectroscopy tool, and I can just start probing a single atom, its chemical magnetic nature around a single atom. That's the level of sophistication we have, right? This is a beautiful slide, actually. Macrostructure is what you just see and quickly say that this could be that. But microstructure is a little deeper and say that, yeah, this is a polycrystalline material. That means the physical properties will not be as good as a single crystal. But then crystal structure is required to understand whether the unit cell formation is there or not. And then atomic structure is very essential in order to look at the interatomic correlation effects. And then comes all the other physical properties. Then you talk about, say, then if this lattice gives rise to a metallic property or a superconducting property, then you have to do electrical resistivity measurement, magnetic property measurement as a function of temperature. Then in different forms, now that's what I was telling. So this unit cell, which belongs to, say, yttrium barium copper oxide, so I can get yttrium barium copper oxide in powder form, in a crystalline form, in a polycrystalline form, and also in an amorphous form. Glass is a perfect example of amorphous because there is no regular arrangement of atoms in glass. Also, in other words, so if you obtain a material in this crystalline form, single crystal form, you look at the scale. It is 2 centimeters here by 2 centimeters, right? Because it has all those It doesn't have a squarish shape, somewhat like a pentagon. So if you take the 1 centimeter square area, or if this whole crystal, whole volume has to be declared as a single crystal, that means from that point to all the other edges, this unit cell is arranged in a perfect periodic way without any misalignments, misorientations, etc. That is a crystal. So to prove that, you need to go beyond X-ray crystallography. Okay, but crystallography is very essential. But so that means a single crystal has how many grains? 1 grain, single grain. Here it is a conglomeration of a large number of such small crystals, right? So this zone is a single crystal, the neighboring one is a single crystal, but the grain boundary is a defect. A grain boundary is a defect in the sense that the regular atomic arrangement is terminated there. The crystal structure formation is not there. So you'll have loosely bound atoms there. So loosely bound atoms are not good for and grain boundaries are also, they could be inlets and outlets for, if it is an oxide compound, for oxygen. So you start losing the interesting properties that a material offers because of the presence of grain boundaries. You can take it that way. So the whole process of first to get a material in single crystalline form or a thin film form is to eliminate these grain boundaries. All right? Good. Yeah. So I'll stop there for today. So, have any questions? Let me just take